Good day, everyone. My name is Candice Tahimic from the University of North Florida. I thank the organizers for the opportunity to speak in this event. Today, I will be sharing some of my thoughts on the future of rodent spaceflight experiments. We are living during an unprecedented time for human exploration. We have made major advances in spaceflight technology that enables us to take the next step in space exploration. As many of you know, NASA is working towards sending the first woman and the next man to the moon in 2024. This mission will be bolder compared to the first US lunar walk in July 20, 1969. In 2024, astronauts will stay on the lunar surface for a week to perform science experiments and to learn more about the moon and our home planet. The knowledge gained from the Artemis missions will help prepare us for crewed missions to Mars in the 2030s. Like most undertakings, there are challenges to overcome. Spaceflight and habitation in extraterrestrial environments present significant challenges to human health. Without intervention, spaceflight as it occurs in low Earth orbit leads to dysfunction and impairments in a variety of tissues. These include neurovestibular, cardiovascular, musculoskeletal, and immune deficits, among others. There are even greater challenges for long-duration missions, since crew will experience prolonged exposure to microgravity, space radiation, and social isolation. As we move towards a new era of space exploration, one of the most important goals is to ensure that humans stay healthy during space missions. As such, contingency plans are in place to enable mission crew and ground support to respond to any critical injuries that occur during space missions. A critical injury is defined as a life-threatening insult to any part of the body. Yet, despite the progress we've made, we still have a lot to learn about how the body responds to injuries sustained in space. Some of my research interests include interrogating how spaceflight factors such as microgravity, radiation, and isolation can lead to bone loss. I will focus on bone in this talk, but the concepts I share today also will be applicable to other tissues and organ systems. Since spaceflight leads to bone loss, an increase in fracture risk is one of the concerns during extended duration missions. Most efforts to understand fracture as it pertains to spaceflight focus on quantifying bone mass and bone mineral density. To date, I am aware of only one rodent spaceflight study that has begun to interrogate the healing process from a bone injury model. This was the recent study conducted by Dr. Casina on one of the rodent research missions and makes use of the segmental bone defect model. However, one of the limitations of the said study is that the injury was initiated on Earth. To date, no major surgical manipulations can be performed in flight. Yet it is thought that the early inflammatory response to skeletal injury can impact the healing process and final outcomes. Given that spaceflight is known to cause immune dysfunction, it is important to test whether the acute inflammatory responses to bone injury are impaired in space. Likewise, we need to better understand how long-term exposure to space affects fracture healing. Addressing these questions will certainly require animal surgery capabilities in the space environment. And lastly, we need to validate the use of anti-osteoporosis drugs during interplanetary missions. In particular, it remains to be shown whether these treatments have any impacts on the fracture healing process in the space environment. I believe that investing in new capabilities for animal spaceflight research can help anticipate human responses to health emergencies in long-duration missions. This in turn builds mission readiness. I see the rodent spaceflight habitats of the future as being highly customizable and able to address a variety of biological questions. These include how tissues respond to and heal from critical injuries, or drug efficacy assessments, or perhaps cognitive studies. I also envision multiple types of habitats to accommodate specific aspects of a scientific investigation. These include modules for long-term housing, surgery, and recovery. These rodent spaceflight habitats will likely take advantage of the tremendous advancements in engineering, manufacturing, and robotic technologies. Some of these are 3D printing, miniaturization technologies, advanced energy systems, ultra-light yet ultra-strong materials, and finally, remote surgery technologies. Advancing animal spaceflight research will certainly require us to look outwards and create diverse partnerships. Fostering these partnerships also should be one of the priorities for the decision makers of the various spaceflight programs. Thank you for your attention.